Good morning, students. In the last lecture, we discussed equation for torque in the terms of moment of inertia. In this lecture, we are going to see the conservation of angular momentum. In class 11, we learn about the conservation of linear momentum, which state that if no external force acting on the body, acting on the system, the conservation of linear momentum takes place. With the same analogy, in the rotational motion, when the external torque acting on a body is equal to 0, the body keeps rotating and the angular momentum remains conserved. Now, we are proving this conservation of angular momentum by taking a equation, vector notation equation of the angular momentum. Here, this vector L is equal to vector R cross vector P. What is vector R? Vector R is the radius vector and this vector P is the linear momentum vector. Now we differentiate this equation. It is dl by dt with respect to time, which is equal to derivative of R cross P. Now we solve this derivative. This is R cross dp by dt plus dr by dt cross P. Now, according to the Newton's second law, we say that the force is nothing but the rate of change of linear momentum. Therefore, the F is equal to dp by dt. Therefore, we can write here vector R cross vector F plus what is dr by dt? Rate of change of radius vector or position vector with respect to time. It is nothing but the velocity vector. Therefore, we can write here velocity vector V cross. What is momentum? Momentum is nothing but the mass multiplied by velocity. And in vector product, when there are two similar terms, the vector product is equal to 0. Therefore, we can write here it is equal to vector R cross vector F plus 0. This is equal to dl by dt. Now, what is R cross F? This R cross F is nothing but a torque acting on the rotating body. Therefore, we can write here this dl by dt is equal to torque. If the external torque acting on a body is equal to 0, that is torque equal to 0, then we can say that this dl by dt, rate of change of angular momentum with respect to time, is equal to constant. And if the derivative of any factor is constant, then the factor is nothing but the constant. Therefore, we can write this vector L is equal to constant. Hence, by using simply a derivative, we can prove this conservation of angular momentum. This conservation of momentum can be written in another form. What is L? In the previous lecture, we say that L is equal to I multiplied by omega. What is I? I is the moment of inertia of the rotating body, and this omega is the angular velocity of the body. This I omega is equal to constant. What is omega? Omega is equal to 2 pi n. So we can also write this I multiplied by 2 pi n is equal to constant. Therefore, from this relation, we can also write this moment of inertia I is inversely proportional to the frequency. So, the conservation of angular momentum can be stated in the different way as this L is equal to constant, either I omega is equal to constant, either I multiplied by 2 pi n is equal to constant, or we can also say that I is inversely proportional to the frequency of the body. Therefore, in this lecture we discuss about the conservation of angular momentum. In the next lecture we are going to discuss the rolling motion of the body. We are going to stop here. Thank you. Goodbye. Have a nice day.